Hello guys, today we'll be talking about quantum mechanics. This will be the first lecture in a series of lectures that I will be doing explaining quantum theory and all that stuff. Alright? So, what is quantum mechanics known for? Well, it's known for this equation. It's called the Schrödinger equation. It reads negative h bar squared over 2m is equal to, where h bar squared, and just h bar is the Planck's constant, alright? And now we have a partial derivative on psi, which is the wave function, over x squared. So we have a partial derivative with respect to x, plus v of x times psi, and v of x is just the potential, is equal to I h bar, where I is a complex number, square root of negative 1, I h bar d phi over dt. Okay, so just going from the beginning to make it nice and simple, negative h bar squared over 2m, this is just a constant. Then you're taking the second partial derivative of psi with respect to x, the spatial coordinate. We're right now we're only in one dimension, plus the potential energy times psi is equal to I h bar, another constant, times the partial of psi with respect to t, which is time. So basically this equation is relating space and time of a wave function. It's showing the evolution of a wave function as time passes. That's why this equation is so famous, because it shows the evolution. It's not just a random equation. It's a fundamental equation of quantum mechanics. Now, what do we want to do? Fundamentally, we want to solve this equation for psi, but that's not that easy to do. So we gotta play around. Now, if you've ever studied partial differential equations before, you would know that a common method of solving these types of equations with second degree derivatives and first degree derivatives, you use a method called, let me write it, separation of variables. What this is saying, we don't need this. What this method is saying is that we have this wave function psi. It's a function of space and time, right? Because it has a spatial derivative and a time derivative. And now has two variables in it, so we can split it up into a function of only space. Let's not call that psi. Let's call that phi of x, and then we have another function of time. Let's call that, what should we call that? Capital psi. Okay, of time. Perfect. Now we can substitute it back into our Schrödinger equation. It becomes negative h bar squared over 2m d squared. Now we have phi, and then another phi, over dx squared, dx squared, plus v phi is equal to I h bar d phi, capital Phi, over dt. Okay, so what have we accomplished here? Right now you can think that we haven't accomplished anything yet, but now this is the trick. We want to divide this whole thing by phi, capital Phi. Now this is where it gets interesting. Okay, sorry for that. So when we divide phi, capital Phi, our partial, let's look at our partial first. So let's just bring out the partial. This is in parentheses, remember? Right here. Okay? So d squared over dx squared. This is only the derivative with respect to x, right? So which one of these is only with respect to x? Well, if you look here, we noted that lowercase phi is only with respect to x. So essentially we can pull out the other one outside the function. So what are we left with? Negative h bar squared over 2m. And as I just said, we can pull this out because we're not deriving with respect to it, so we can pull it out. Okay, and now we just have d squared phi over dx squared. And then we're left with the same v phi, capital Phi, is equal to, now this is with respect to time, and the time part is the capital, so we can pull out the lowercase because it's essentially another constant. So we have phi over ih bar, and then we have d capital Phi because it's with respect to time. Okay, now as I said, we were going to divide by this separation of variables right here. And what do we do when we divide that? And essentially we're doing this because we want only one variable on either side of the equation. Like for example, here we have a capital and a lowercase, capital and a lowercase. We don't want this. We just want lowercase on the left and capital on the right, something like that. So we get negative h bar squared over 2m, and when we divide capital Phi divided by lowercase and capital, we just get 1 over lowercase. And then we get d squared over dx squared. And when we divide this, it just becomes 1. So we have v equals ih bar. What's phi divided by phi capital Phi? Is just 1 over capital. And we still have this partial with respect to time. Alright, so now this is where our really neat trick comes in. We have a spatial part on the left with variable only of lowercase phi, which is only of x, spatial dimension. And we have a variable on the right only of capital Phi, which is a time dimension. And we're claiming that by the Schrodinger equation, these two quantities have to be equal. But how can a time derivative be equal to a space derivative? They can only be equal if both of their values are a constant, and we'll call that e. Well, you'll find out later why. So, if this is equal to e, and this is equal to e is equal to e satisfies the equation, right? So now, if we just rewrite what I just said, that we separate the left and right side of the equations into our separation constants e, we get negative h bar squared over 2m, and then 1 over phi d squared phi over dx squared plus v is equal to e. Fair enough. And now for the other side we get, I'll call this equation 1 by the way. For equation 2, we can get ih bar 1 over capital Phi d phi over dt is equal to e. Right? Because they're both equal to the separation constant e, that means they're both equal in the Schrodinger equation. But I want to pay attention mainly on this second equation, because it's something that we can actually solve. You can notice in the first equation that we can't solve it because we have this potential v, and we don't know what it is yet, but if you designate a specific potential, then we can solve this equation, which is known as a time-independent Schrodinger equation. But we'll find that out in due time. Okay, so let's look at equation 2. ih bar 1 over capital Phi d phi over dt is equal to e. I'm just going to start off by multiplying by capital Phi on both sides. It's going to cancel them out, right? So we're going to get ih bar d phi dt is equal to e capital Phi. Okay, And now I'm just gonna divide by IH bar on both sides, and we're gonna get d phi, capital Phi, over dt is equal to E phi over I h bar. Okay? And now, since we have an imaginary, let me just bring this here. Since we have an imaginary number in the denominator, we don't really like this. So we're just going to multiply by I over I, which is essentially 1. So we're going to get d capital Phi over dt is equal to, I should be saying partial phi or partial t, but my language is kind of sloppy. So I squared is just -1, and we have this I in the top, so we get -I over h bar times E times capital Phi. And if you've ever seen this before, we have a partial with respect to time of phi is equal to some constant times the actual function. And this is a commonly found solution because we know the solution already. We just integrate both sides and we get that phi is equal to e to the I et over h bar. And this is very important. And you can kind of see it because if we're integrating this and we have e phi, and then if we derive this, take the derivative if this all comes down and then you subtract it because the derivative of e is just itself times the derivative of the inside. So you can see where this comes from. Now this is very neat because if you remember, we started off with this psi of x and t, and we separate it into phi of x and capital Phi of t, correct? And now we just solve for this capital part, which is the time part. So what do we get for it? We got that it was equal to e to the I et over h bar, and we still have this phi of x. Now E is our separation constant, but it also represents the energy of the system, of the wave system, the wave packet, whatever you want to call it. And this is pretty cool. We started with this arbitrary function phi, and we've broken it down into a spatial part and a time part, and we've actually solved for the time part. So that means no matter what wave function you have, the time part will always be the same, e to the I et over h bar, and that's how the wave function evolves over time. But the space part is a little bit different, because we have this time-independent Schrodinger equation, because you see that in this equation there are no time dimensions, it's time independent, while as in this equation we have a time dependence and the spatial dependence. So for equation 1 that I have over here, I'm just going to multiply everything by phi so I can get rid of it in the denominator. I don't really like it like that. So we get this and this is the true time-independent Schrodinger equation. Oops. Time-independent Schrodinger equation. And these are the two fundamental equations we're going to work with. We already know how, we just found out how a wave function evolves over time according to this exponential. And now, for a given potential V, we can find out how it evolves spatially under this time constraint.